Okay, so hello everyone, and welcome to the first tech colloquium of the semester. I'm very happy to take over from Jane and run it right now. Unfortunately, because of the changing situation with Omicron, we're not able to be in person, at least yet. Hopefully, partway through the semester, we'll be able to start having hybrid meetings where some of us can meet in person and others can join by Zoom. So keep tuned for that. Today, we're very lucky for our first talk of the semester to have Manuel Kauers from the Institute for Algebra at Johannes Kepler University in Linz. So Manuel received his PhD from RISC near Linz in 2005, and he has a long list of accomplishments, including being co-recipient of the AMS Robbins Prize for his resolution of the QTSPP conjecture using computer algebra techniques. He also has a very nice textbook related to symbolic computation, combinatorics, and enumeration. And today he's going to tell us about guessing with little data. So please go ahead, Manuel.
Okay. Thank you, Steve, for the nice introduction and also for the invitation. And thanks to all the others for coming. So I'm going to talk about guessing. I wasn't really sure how familiar this is to this audience. So let me just start slowly. And what is always easy to do is throw away information. So for example, if you have a square, an exact square, then you can discretize it and round maybe the coordinates and you are getting an approximate square. That's an easy thing to do. It's much more interesting, however, to go the other direction. If you have such an approximation of a square, then to recognize that actually that was a square, because for this direction you have to, it seems that you have to invent information that has been deleted before. So this is the general idea behind automated guessing. And automated guessing appears in several different flavors. So let me give you a more concrete example. It's also very elementary and similar. If you have if you have an exact number like a third, then it's easy to throw away information, or you just convert it to a floating point number, and then you don't know anymore that it was 1/3. You just know it's something somewhere in this area. And the interesting question is, again, how do you get back? How do you get back from the approximated number to the exact number? And of course, somehow logically, strictly speaking, that should be impossible. And yes, it is impossible because the information has to come from somewhere. It cannot come out of nowhere. But what you can still hope to achieve is to get an idea that this floating point number that you have on the top is close to the exact number that you have at the bottom. And this is actually something that can be done computationally. In this case, you can do it just by looking at it and you will see it immediately. But in this case, it's maybe not so easy anymore to recognize that this is close to 4/7. So that would be an instance of guessing. You recognize from some approximate data hypothesis, at least, of what it could have been before it was approximated. For this guessing instance, there is an algorithm which does this. I'm not sure how widely this is known. It's a very classical thing. It has been known for decades, and it's an essential algorithm in computer algebra, but it's not so widely taught. So maybe if you haven't seen this, then this is then you will see it now. And if you have seen it, then you will certainly enjoy seeing it again because it never loses its magic. So here's what this LLL algorithm does. It takes as input a basis of a lattice. So that's an integer lattice, and that would be a basis, just two vectors, and L is the set of all points that you can write as integer linear combination of the basis vectors. So these are the yellow points. And so the two yellow vectors would be the input of this algorithm. And as an output, you will get a basis that generates the same lattice, but that consists of short vectors. So for example, of those two. I don't want to make this formal. It's not necessarily the shortest possible, but somehow close to the shortest possible. And for doing the guessing that I had on the previous slide, you can formalize this as an LLL computation problem, because what you really want is you want to have two integers such that the difference between the exact ratio of these two integers and the approximate number that is given is small. So that means that this is epsilon. Put this on the other side, and then you scale this up to make these floating points into integers. And then epsilon is something small, and 10 to the 7 is something big, but if you multiply them together, then it will be something of a reasonable size. So let's call it R for reasonable. And then what you have here is an equation where you are searching for small p, q, and r integers that satisfy this integer relation. So that means you are searching for a vector that is in the lattice that is generated by this vector and this vector. So on the bottom you see this number and this number. And here you're somehow asking what is the linear combination of those that makes this R. And then here the 1 and the -1, they make sure that you get here the P and the Q. So this is a short vector in this lattice, and LLL can find this short vector for you. So this is how this guessing instance works. Here's another another instance of automated guessing. That's what maybe is more commonly understood as guessing. Here's again, first the forward direction. If you have a recurrence and an initial term, then it's very easy to generate terms of the sequence. So these would be the Catalan numbers, because all these terms are determined by the initial value and the recurrence. And guessing is the opposite direction. You have some finitely many terms, and you want to get the recurrence from this. Okay, so again, that's logically impossible because we have no chance to know what is the next term. It could be anything. But the idea is you want to derive a plausible conjecture about what the recurrence could be based on the data that you have. And in this case, the standard approach is to do this with linear algebra. So you just make an ansatz for a recurrence. You just suppose it has a recurrence of order 1 and polynomial coefficients of degree 1 also. It's a very simple example. And then the task consists in finding these coefficients of these recurrences, of these coefficients, and the coefficients of the coefficients. And then you have, you know what the A's are for the first few n's, so for n equals 0 up to 6, and you can just plug this in and evaluate. And you can also evaluate the n itself, and then you get linear constraints on the unknown coefficients. And if we have enough data, then we have more equations than variables, like here. And then we wouldn't usually expect that this has a solution. So this is a linear system that any true recurrence must satisfy, because that's what it means, that it satisfies this recurrence, that this is true for all n. If it's true for all n, it must be true for these n's, and that's what we are asking here. We don't expect any false solutions because it's unlikely that an overdetermined system has a solution. So that's the reasoning. If you have more variables than equations when you play this game, then you don't expect a solution. So if you nevertheless get a solution, then you somehow believe that you have really found a recurrence that is valid beyond the data that you have. Okay, so how can we ensure that we have more variables than equations? More equations than variables. Suppose we have n terms that are given. And suppose we want to find a recurrence not of order 1, but of order r. And with polynomial coefficients not of degree 1, but of degree d. then this is the number of variables, and that's the number of equations. So you have to subtract r here because the recurrence contains n plus r, and you want to evaluate that, and so you don't want to get an out of bounds error. So you have to subtract this here. So in the end, this is the condition. So you are free to choose or to test for a recurrence of order r and degree d, provided that your choice of r and d is so that this expression, this product here, is less than the number of terms that you know. And this restricts your search space. So this is the search space. You can search for any order of the recurrence and any degree. So that would be a recurrence here of order, I don't know, 20 and degree something. And there's the hyperbola that's determined by this equation here that says if you have 20 terms, then you can search for any pair RD that is below this hyperbola. And of course, if you have more terms, for example, 100, then you can search for a bigger range. And if you have even more terms, then you can search for an even bigger range. If you search for something that is above the hyperbola, then you would get an underdetermined system, which always has a solution. So then you can't draw any conclusions from this, because there will always be some fake solutions that just exist because the system is underdetermined. And the true solutions, if there are any, they will be among them, but you will not be able to distinguish them. So you will test for choices of R and D that are below the hyperbola. That is determined by the number of terms that you have. So that's what you can search for. And that's one half of the story. The other half of the story is where are the equations. Of course, that depends on the example and on the application where the sequence comes from. There might not be any equation, then you can search for very long and generate a lot of data and never find anything. But there's a common pattern that is maybe good to keep in mind. And that's that the true solutions, they are aligned also in form of such a hyperbola. So for a certain, if you fix a certain sequence that has some meaning, then what you typically observe is that that sequence has such a blue hyperbola with it. And the meaning of the blue hyperbola is that for every point above the hyperbola, that sequence satisfies a recurrence of this order and degree. So for the blue hyperbola above it, there exists. And for the yellow hyperbola below it, we can check. So in this example, if we have 100 terms, then we would be lucky here in this range, because that's what we can investigate and where there also exists something. Okay, so that's the standard setting for automated guessing and searching for recurrence equations. And the question I want to discuss now is, what do we do if we don't have enough data? So if we don't have if we are, for example, in the situation where this is the truth, this is where the true equations sit, but we only have 20 terms. And I said before, we can only investigate this, but there's nothing here, even though there is a recurrence, and it would be cool if we could find that somehow nevertheless, despite of this restriction. Okay, so that's the goal. So how can we do this? The idea is that correct equations, they are somehow more nice than a generic solution of the linear system. If you just have an underdetermined linear system, which you get when you search for something that is above the yellow curves, you get an underdetermined system, and it will always have solutions. But somehow these solutions, the solution space consists of fake solutions and true solutions. And the question is now, how can we distinguish them? So the true solutions are somehow, we recognize them because they are nicer than the generic solutions. And what does nicer mean? Yeah, that can mean different things. So for example, one feature that you expect from a correct recurrence of an integer sequence is that if you apply the recurrence to the given data and compute the next few terms that you don't know, then, well, you don't know what the next few terms are, but you know there must be integers. So if the recurrence doesn't produce integers, but some rational numbers, then it's not the right recurrence. So, and at the same time, that's what you would expect from a generic solution. A generic solution is very unlikely to produce integers if you continue it. So that's a strong test. If you have a recurrence, you're not sure, you found something with guessing, you're not sure if it's true, but if it continues to produce integers, well, that's a good indication that you found something that is true. So that's one thing. So we could try to search in this whole space of containing true and false solutions. We could search for those solutions that correspond to recurrences which continue the given data by integers and not by rational numbers. That's one idea. Another idea is to look at the singularities. So here I'm talking about recurrence equations, but you can equivalently search also for differential equations satisfied by the corresponding power series. And then in many applications, you know beforehand that this differential equation, if it exists, it will have nice singularities. So if you have solutions that correspond to a differential equation that have bad singularities, and then you can discard them. So then we have again some idea of how we can separate potentially trustworthy solutions from things that we don't believe and that we would like to discard. There are some other things. So I don't want to define what p-curvature is, but it's a certain notion, certain matrix that you can associate to a different differential equation, which has the property that usually if the differential equation has a meaning, it comes from some application, and usually that matrix is nilpotent. That's something that you can check. But if you have just a random differential equation, then it will not be nilpotent. So here, this is again something where we can distinguish nice elements of the solution space from not so nice ones. And another idea is you can look at the coefficients. So the integers that appear as coefficients of the polynomial coefficients, what you observe in practice is that usually they are smaller than you would expect from a generic solution. So all these things we could in principle try to search, to restrict the search space. But it's not so easy how to do that for the first three, because if you try to somehow translate these conditions into equations, then you are led to nonlinear equations and maybe even Diophantine equations, and we don't know how to solve them, or at least efficiently. But the fourth one is a good one, because the fourth one is something that you can do with LLL. So LLL is exactly the thing that I explained in the beginning that tells you in a vector space or in a lattice, what are the elements that have short coefficients. So that's exactly the question here. So let's see if this works. Here's a simple example. I've chosen just a relatively simple one so that it fits on the slide. This sequence defined by this binomial sum satisfies a recurrence of order 2 and degree 2. Degree means polynomial coefficients of degree 2. So according to the formula from earlier, you expect that the linear algebra approach would need 12 terms for solving, for finding this recurrence. And it's the 2 plus 1 times 2 plus 2, that's 12. And now let's suppose we don't have 12 terms, we know only 7 terms, the first 7 terms. So from 6 to 0, is there a question? So suppose you have only this amount of terms, then you can still make an ansatz, and that's what we do for recurrence of order 2 and degree 2. But now it's underdetermined because we can get only 5 equations with this 7 terms. So now let's look at the solution space. It will now be high-dimensional solution space. And let's not look at it as a Q vector space, but let's look at it as a set module. So you can get a basis for the set module, not with Gaussian elimination. You have to use some more advanced stuff. You can do this with the Hermite normal form. And there are people in the audience who know very well about how to compute Hermite normal form. So you can ask them how to do this. If you do it, then this is the result. So, and then you see there are long integers and short integers, but then you apply LLL to this, and then it will make the coefficients very small because that's the job of LLL. And then you find the first vector in the LLL basis, which is the shortest. That's exactly the right recurrence. That's indeed the recurrence that this sequence satisfies. So that works. So how far can we go? Does this work only in this example, or does it work more generally? Okay, so classically, this is the number of terms that you need to find the recurrence. And the question is now, or we have seen in at least one example that we can get along with fewer terms. And the question is now, how many terms do we need now? What should we replace this formula by? And I don't have really an answer that is as explicit as this nice formula that we get in the linear algebra case. But I have some kind of answer, actually two kinds of answers. So there's a somewhat theoretical answer and a somewhat pragmatic answer. And the theoretical answer is that what we can figure out is how big do we expect the coefficients of a generic solution to be. And then the coefficients of the true recurrence must be smaller than that if we want to find it, because if it's larger than that, then LLL wouldn't be able to distinguish them. So LLL can only distinguish the good ones from the bad ones if the good ones are the smaller ones. So the good ones should be smaller than the generically smallest ones. So what is known about the size of generic solutions? There's an old result that's known as Siegel's lemma, which says for a matrix which has more columns than rows, that there exists a non-zero solution vector, a non-zero vector in the kernel, which is not more than some expression in infinitum long. So the size of the coefficients of this solution vector is bound by this expression. So if we apply this to our setting, then we would fix the number of terms n of the known sequence. And we have to also assume that we know a bound on how big these terms are and that they are integers. And then we fix an r and a d. And then if we plug this into here, then we get this expression. Just follows immediately from here that you get a bound on the number of solution that exists in any case, or regardless of whether a true recurrence exists or not. Such a solution you will always find. And if you look a bit closer at this expression, you will see that if you fix n and r and you let the d grow, then this converges to 1. So that means if you keep searching, if you keep playing this game with LLL and you increase the d, then at some point it doesn't make sense to continue, because at some point you will have certainly a very short vector. And if it's certain to have one, then you cannot trust that this is a meaningful outcome. So that's the interpretation. So unless the length of the coefficients of the two recurrence is significantly shorter than this bound, we cannot expect to discover this. So on one hand, because this converges to 1, you can derive from this an idea of how far would you reasonably go with the degree before you say, well, I give up and I'm not going to find anything meaningful. Somehow this would correspond a bit to what in the linear algebra case the yellow hyperbolas did. they said don't search above the hyperbola, and this somehow corresponds a bit to this. Another thing is that you can use the difference between the length of the shortest vector that you found and this bound as a confidence measure. Maybe not the difference, but the ratio. The smaller the shortest vector is that you actually find in an example compared to the bound, the more confidence you will have in that you found something that is not just noise. Okay, so that would be the theoretical answer. And the pragmatic answer is, well, just try it out on some examples. So
can I ask a question, Manuel?
Here we go, yes.
Just before you switch topic, so there is this convergence with D going to infinity. What if you are guessing recurrence with constant coefficients? Then what theoretical answer would be? If you are guessing recurrence, but with not with polynomial, with constant coefficients.
Yeah, then yes. So then you don't have so much, then you don't have so many degrees of freedom, because the degree is just bounded by, it's just 0. And then, yeah, you can do Berlekamp-Massey, which would correspond just to the classical thing. And I don't think that you can go much beyond this. I don't think it will help you to play this game with LLL, or yeah, maybe you can go a little bit further, but I think it's more effectful, the idea when you have polynomial recurrences, polynomial coefficients.
I understand. So you have 2 dimensions, you have freedom.
Yes.
Yeah, okay.
Yes, so then you can move around in the plane and search for where it works best. And if you are stick down to the axis, then you can just move left and right. And that's, yeah, that's maybe not enough.
Okay, thank you.
Okay. Okay, so we just tried this out. We collected some examples that come from lattice walk counting, and we took examples for which we knew that a recurrence exists, and we compared how many terms do we need to find them by linear algebra, and how many terms do we need before this LLL-based approach succeeds. And the outcome is that if in the best case, you can drop about 50% of the data. Yeah, so a more specific answer is in this picture. So here's the amount of data that you need in this range, or in this range, or in this range, and this is the number of examples that fit into this range. So this means for 30% of the cases that we tested, you need between 50 and 60% of the data, and for more than half of them, you can get along with 60 to 70% of the data. And you never need, so you can always drop in the cases that we consider, you can always drop at least 20% of the data. So if we try to plot this into this picture from before, and we are optimistic and take the 50% bound, then this means with 20 terms, instead of going in this, being restricted to this area, you're now restricted to this much larger area. So, and Eugene, you look here at the bottom. You still can double, but I'm not. So in principle, you can still double, but I don't think it will be very successful here. I would rather try it here. Okay, and here for 100 and here for 500. Now you might ask, if we don't find a recurrence because we don't have enough data, then why don't we just compute more terms? Well, usually in examples that we do when we work with lattice walks, we play this game, this classical linear algebra game with thousands of terms. So if 5,000 terms are not enough, then we just compute 1,000 terms more, and then we try it with 6,000 terms. So it seems that for this kind of examples, this LLL-based approach is not really useful. But there are other sequences where you can't just compute thousands of terms. There are very difficult sequences of which we don't just know very much. And a famous example is this one here, the number of permutations that avoids this pattern. Never mind what this means. If you're not familiar with this, it doesn't matter. It's just a famous example of a sequence which is pretty hard to compute. So we know the first 50 terms, and the sequence has been investigated for decades, and that's all we know. No, we know a little bit more about the sequence, but we don't know more than 50 terms. And there's a quotation by Zeilberger that says not even God knows the 1000th term of this sequence. So certainly people have tried to recover a recurrence with linear algebra from the 50 terms, and 50 terms are not enough to do it with linear algebra. And you won't be surprised to hear now that LLL also is not enough. So that corresponds to a search with 100 terms. And yeah, sure, we didn't find anything because that would be too simple. But what about less prominent examples? So what we've tried is we looked at the OAIS, the Online Encyclopedia of Integer Sequences, which at the moment contains 350,000 sequences. And they have keywords for the sequences, and one of the keywords says hard. So there are 7,500 roughly, which are labeled as hard. And this is supposed to mean that the next term, the computation of the next term would need a crazy amount of computation time, or maybe even new theory. So most of these hard sequences, they come from a very obscure number theoretic definition, and we wouldn't expect them to satisfy a recurrence. So to reduce this number a bit further, we dropped all the entries whose description contain the word prime, because we think they have no chance to be p-recursive. And then there are still 3,800 survivors. And then some of them have very few terms. So some of them have just one or two known terms. That's certainly not enough to do any guessing. So we restricted the search to those that have at least 30 terms. And the upper bound is not so essential. In 90, there are not many entries here that have more than 90 terms. And so we applied then this LLL-based approach to these sequences. So to do this systematically, you also have to automatize the when you will accept a guess and when you will reject it, because the systems are underdetermined. You will always find solutions, and among these solutions there will always be a shortest one. So and there's no such thing as nothing found in this setting, but you have to say, do we trust the thing that we found? And we use then one of these other criteria. So we took the shortest vector for a certain R and a D, and then used the corresponding recurrence to generate the next 10 terms of the sequence, and then checked whether this produces integers. If it doesn't produce integers, it's certainly wrong. And if it does produce integers, well, then it's suspicious. Then we look at it. And that was the case for about 20 sequences in this pool, which we then looked at one by one with our eyes. And we rejected 18 of these 20 hits because, well, they were somehow suspicious in one way or another. But then there are two left where we think we found something that is meaningful. And I want to show you these two cases where we found something. So this is one of them. It's the AN is defined as the number of permutations of length n, which is such that kn plus 2 is mapped to a number that is not 2 more than what k is mapped to. Okay. So these are all the numbers that are known, all the terms that are known about the sequence. Yeah, so it's there's a Mathematica program also on the OAIS with which this was computed, and you can roughly say that the computation of each term is about twice as expensive as the computation of the previous one. So it goes exponential, and you can see that at some point you will hit a wall. You can't go much further than this. And this data is not enough to find the recurrence with linear algebra. Oh yeah, first here for illustration, this term here is 5. That's the third term, for which there are 6 permutations, and the term is 5 because the last one is the only one that is ruled out, because 3 is 2 more than 1. So that's what is not allowed. That's what is excluded here. All the others survive. That makes it 5. So we found a recurrence of order 10 and degree 6. And we think it's correct. Why do we think it's correct? Yeah, there are several reasons, some of which I've already mentioned as potential reasons. So for first reason is that in the LLL basis, the first vector is much shorter than the second vector. And you would typically expect that they are all somehow equally short. But if the first one is shorter than the others, that's an indication that this has somehow extra meaning. Another thing that adds evidence for the correctness is that if we don't take all these 36 terms that are known, but remove some of them, then we keep finding the same recurrence. So we can remove quite a lot of terms. So we can get already with 29 terms are enough to find this recurrence. So that is also something that you wouldn't expect generically. You would expect that you will always find some other noise if you do this with different number of terms. Another very strong evidence for the correctness is that if you look at the operator that corresponds to this guessed recurrence, then it has a right factor of order 8 and degree 11. How did we find this? So we found this by taking the guessed recurrence, we used it to generate a lot more terms. They all turned out to be integers, not just the next 10, but even the next 200 or so. And then we had a lot of terms to which we could apply the linear algebra guesser. And with the linear algebra guesser, we could find all the recurrences that are satisfied by this hypothetical sequence. And then we found it satisfies even a shorter recurrence, shorter in terms of order, but with higher degree. And that's not likely to happen. If this was a garbage recurrence, then this computation would yield back exactly this recurrence and not one of shorter order. And then we made a lot of effort to compute 4 more terms of this sequence using the Mathematica program that is provided in the database. We optimized it a little bit, and we computed 4 more terms, and they matched the predictions of the guessed recurrence. So that's not anything that you expect from a garbage recurrence. So this is really, to me, this is very convincing. We are pretty sure that this guessed recurrence is correct, but we didn't try to prove it. So it also, this definition, it doesn't look so obscure that you wouldn't believe that this satisfies a recurrence. So the definition also looks like that's something that could satisfy a recurrence. Here's another one, or here's the other one of the 2 that we found. It's very different. That's more number theoretic. So here the AN is defined as the number of integers, k, such that both k and k square are palindromic when you write them in base 10, and k square has n digits. So in this case, 70 terms are known. Here they are. So it looks a bit different. The numbers don't get too big and there are lots of zeros. And so look, for example, at this one. That's the 15th term in the sequence. And the term is 9 because these are the 9 integers that are palindromic and whose square is also palindromic and where the square has 15 digits. So in this case, we found a recurrence of order 6 and degree 9. And it turned out that once we had the recurrence and we looked at the recurrence and we found out, oh, this can be solved in closed form. So it admits a so-called quasi-polynomial as a solution. And here it is, the conjecture that is implied by the recurrence, but the recurrence is guessed, so the conjecture is also just guessed, is that the AN has this closed form. Now, I don't have a lot more empirical evidence for why this guess might be correct, but there's no need for empirical evidence in this case because, yeah, we just proved it. Once you know that this is a potential answer, then you know what to prove, and then you see, oh yeah, actually that sequence is not as hard as the authors of the sequence thought. So in this case, we really found something new. Okay, that is all I wanted to tell you. Let me just quickly summarize. So guessing is a well-known and classical tool in experimental mathematics, and I'm sure many of you are familiar with this and have used it many times. And the more terms you have about a sequence, the better it works. But sometimes you just don't have more terms and no option to compute more terms. And when you don't have so many terms, then the linear algebra guesser can overlook equations, even if they are of reasonable size. So what I did is propose a way to reduce the amount of data that you need. And by using features of the equations that you are looking for that the linear algebra approach doesn't see. Now, the feature that we used is the coefficient size. And that seems to work, and at least in some examples. What remains open is there are some other features that I listed, and where we didn't see how to do this idea with these features, like the structure of the singularities, for example, because they lead to nonlinear equations. But I wonder if these nonlinear equations can be avoided, and there's also perhaps an efficient way of specifically looking in the vector space of solutions for equations that have some of these other features, because that would allow to reduce the amount of data even further. Okay, that's all. Thanks for listening. And thanks
okay, let's thank Manuel for his great talk. Are there any questions?
Yeah, I have questions, sorry. So I just don't see immediately. Does it extend to the case when your samples, sample value are not necessarily integers, like non-integer sequences?
Yeah, it works for rational numbers also.
Algebraic?
Yeah, well, then it gets a bit messy. I think you can do it for, yeah, well, no, I didn't think about algebraic. I think you could do it for polynomial sequences. So yeah, for sequences of polynomials. And then you wouldn't use LLL, you would again use linear algebra.
So you want definite domain? Well,
yes.
sequence.
Yes.
So if sequence is not definite, there are no chances to. Yeah. Oh.
No, sure. This is all about linear recurrences with polynomial coefficients.
Mm-hmm. Okay. Thank you.
Any other questions? So I have a question. Is there an implementation that we can use if we want to try this ourselves?
Yes, we have an experimental implementation, but it will go public soon. It's not yet published.
Okay.
But yeah, you can have it. It's not a secret, and it's not very hard to program. This is just so much code. I don't know if you can see this so much.
And I know there have been some sequences, for instance, in lattice path enumeration, where you have tried guessing before and it failed. Have you used this new approach on recurrences you've seen, or on sequences you've seen previously where you couldn't find recurrences?
Yeah, well, that was the original goal. The motivation for this was to do exactly what you suggested, specifically for the 4D walks, which we recently analyzed. Because for 4D, you really can't compute a lot of data. We had 700 terms. And unfortunately, LLL is too expensive for this. So if you have 700 terms, I wasn't able to run the LLL through this. So this really works well if you have just 100 terms or so. And 700 terms is, yeah, it's much more than 100. And so, and that would be for 4-dimensional walks. And if you have lower dimensions, like 3 or 2, well, then it's easy to get thousands of terms. So then it's even harder to get the LLL computation through. That's one point. The other point is that what we often do in the linear algebra approach is we guess, we generate the data only modulo prime and then do the guessing modulo prime. But if you want to do this with LLL, you really need the integer terms. So then that makes also the generation of data more expensive because you have to do Chinese remaindering. You have to do this as often as the longest number is long. That can be quite a lot.
Yeah. Okay. Any other questions or remarks for Manuel? No? Then let's thank the speaker again. So I will stop the recording.